Hello everyone. Today we will talk about Wittig reactions. Wittig reactions. So this is a very simple reactions. This can be utilized to make make an alkane, right? So all we need for this reaction is obviously a carbonyl group, which is a part of either aldehyde or ketone. So let's say if we have an aldehyde, and then this aldehyde will be reacting with a phosphonium halide. Uh, so this is something new that you haven't heard before. So these are a compound that looks like something this. So this is a triphenyl phosphonium halide. So this is going to be connected to CH2. This doesn't have to be CH2. This could be any carbon chain, by the way. But it's most often used as a terminal alkene that we cannot make on our usual strategy. All right, so what's gonna happen is the reaction is pretty simple. Like all that's going to happen is you eliminate this portions. So the double bond then snap back in. So the reaction's gonna give rise to, so then it is going to be CH2. So the side product for this reaction is going to be triphenyl C6H5 3 phosphine oxide. So the oxygen is coming from our carbonyl group. So this reaction, the mechanism for this reaction is goes through a 2+2 like cycloaddition reactions. It happens in a concerted manner. So let's talk about the mechanism for this reactions. So this is our triphenyl phosphine oxide, and this is our phosphonium halide. You can call it triphenyl phosphonium. Let's write down the full name. Halide. Okay, so usually the halides are so let's draw the mechanism now. All right, so usually halides exist in resonance form. So the halides can exist like this: cis6h5 3 p ch2. So this is in resonance cis6h5 3 p. So if I move this pair of electron towards the carbon, so how does our molecule gonna look like? It's gonna look like CH2 minus, and then this one would be our plus. So obviously you observe here that the carbon atom has excess negative charge. So what does that mean? So let's look at the reaction here. So let me write this one down: RCOH. And we all know that the carbonyl carbon is going to be our delta positive and the oxygen is our delta negative. So if I put my halide right next to it, can you guys tell me which one gonna react where? So let's say this is CH2 P C6H5 3. So this portion is plus and this portion is negative. So if I put my phosphonium halide right next to it, so obviously the negative portion is going to react with the positive carbon center, and the negative oxygen is going to react with our positive phosphorus ions, phosphoneum. So you will create a 2+2 cycloaddition reactions. So our intermediate is going to look like something like this. So let me color code this so that you will see the difference. R so we have R, C, H, O. Sounds good. So let me color code the new bond that we just formed. And the old we had was P, BH2 on this one. Are we good so far? All right. So this is a 2+2 cycloaddition reaction where you made a cyclic ring. So now it will be just a rearrangement of electrons. So basically what's going to happen is you're going to be breaking the CO bond, which will move back there, and you will also bring back this one as well. So this is a cycloaddition in a concerted manner, so everything happens together. So that will gives us the product that will look like this. Okay, this is not one of the prettiest picture. Maybe let's make it pretty. Why not, right? R, C, H, double bond O, not O, CH2, right? And what would be on the other side? On the other side, you will have oxygen. So let me draw it right on top of it so that you will know. Oxygen, P, C6H5, 3, phosphine oxide. Oops, sorry. Phosphorus was white. Yep. So this is a great reactions to make the terminal alkene that you couldn't make in our earlier type of elimination reaction where this terminal alkene would be a minor product. So if you remember from our earlier example from your organic one, let's say if you have something like this, and since this is a tertiary alkyl halide, and then we have a strong base here, so that would give rise to an elimination product, and our elimination product would be, you're gonna have a alkene where instead of having a terminal alkene, you're gonna be forming this alkene where it's gonna be within the ring, because this is the more substituted alkene. So this is a more substituted alkene, hence it's gonna be our major product. So this is going to be our major product. So what would be our minor product? The other product that you might have expected is a terminal alkene. So this one here is going to be our minor product. But now, after knowing the Wittig reaction, can you guys design how to make our minor product? So let's say I want to make the product on the right side. Let's say I want to make this product B. I want to make the product B. I don't want to make A. So do I have to follow these reactions? Of course not. So how can I make this minor product as my only product? So very simple. Let's say you want to make this reactions, right? So all you have to do is do a Wittig reaction. So and our Wittig reactions, what are the ingredients that you need? We need a carbonyl group. So we need a ketone. And then what else do we need? We need a CH2 group, right? CH2, P, C6H5, 3. and that's it. So if we have this as our ingredient, then these two would get combined, and then we're gonna be having this terminal alkene would be a major product. So if you see a questions like this, how to use Wittig reactions to make such alkene, all you have to do is, break the C double bond C, separate them out. That's pretty much what we did, right? So across the double bond, you have two carbon atoms. So we just separated them out and then add oxygen on one side and other side triphenyl phosphorus. That's it. P cis6H5 3. So this is how you should approach the Wittig reaction problem. So do you want to do another one? All right, so let's do another product. How can you make this product? Well, this looks exactly the same. Let's make it something different. All right, how can you make this product? So again, the strategy is pretty simple. You just have to separate the double bond C. So let me separate them out. And then on the other side, so let's just add oxygen on one side and triphenyl phosphonium halide on the other side. And that's pretty much it. So in terms of retrosynthesis, so we can make that product by Wittig reactions. So we can make that product and there we go. So this is a very quick strategy to make alkene. So the way the phosphonium halides are being made is, I'm not gonna ask this on exam, but you should know why these are good. So what happened is, if you have a triphenyl phosphine, and then you have an alkyl halide. So this is best if it's primary or secondary. So it's not, so obviously you cannot do that if it's tertiary, because the reaction that happens at this point is a SN2 reactions. So right now phosphorus has 4 bonds because it has give away the electron, so it should have a positive charge. But still the molecule is not ready yet. So right now we need a strong base here. So this proton here is an acidic proton. And this proton, the pKa is around 35 for this one. This is right next to a phosphonium ion. So it's the pKa for this proton is around 35, if I remember correctly. So this proton can be easily removed if you use a very strong base like butyl lithium. Like if you have, this is the one they commonly use, CS2. So this is butyl lithium, right? So this is a organometallic compound. This is highly basic, so this is a very strong base. So this base can abstract your proton, so you can make cis6h5 3 p plus ch minus and ch3. Now this is our phosphonium halide, right? So you can neutralize the positive charge on phosphorus by bringing this back. So this is a resonance structure is going to be cis6h5. And that's it. That's how we make our phosphonium halide. All right. Any questions? Feel free to let me know.